Hello dear students. So we were discussing about the order properties of R. We had proved several results in the last lecture. So there are a few more which we will like to prove. Yeah. So we have seen that 1 is greater than 0, right? We have seen that 1 is greater than 0. And also we have seen is n greater than 0 for all n belongs to natural number. Okay. So let us try to construct some other some other real numbers which are which we can say they are positive. Okay. So suppose we have 1 by n where n belongs to natural number. Okay. So let us suppose this number. Let us check whether this 1 by n is a positive number or not. Okay. What is 1 by n? 1 by n is the multiplicative inverse of n. Multiplicative inverse or reciprocal inverse of n. Okay, this is what we will try to show. So suppose that 1 by n is less than 0. Okay, then what does it mean? It means that minus of 1 by n is greater than 0. Okay, this is there. Now since n is greater than 0, we already know this result, we have proved it by induction. N greater than 0 for all n natural numbers, right? This is in n. Okay, so since n is greater than 0, so by order property, so order property will give us that the product of these two, okay, by order property of R, we have n into minus 1 by n. This product has to be greater than 0. Okay, product of positive numbers is positive. This is one of the order properties. Okay, the first order property is sum of two positive numbers is positive, product of two positive numbers is positive. There is the second one. The third one is the law of trichotomy. Okay, so only these three are the order properties. So n into minus 1 by n, that we know it's minus 1, so we get something like minus 1 greater than 0. Okay, but this is not true, but this contradicts 1 greater than 0. Okay, 1 is already greater than 0, we know, so this actually contradicts our result. Okay, thus our assumption was incorrect. We had assumed that 1 by n is less than 0. Okay, so thus 1 by n has to be greater than 0 for all n belongs to natural number. Okay, so given any natural number, 1 by n is always positive. Okay, right? So the numbers like half, 1/3, 1/4, they are all positive numbers. Okay, these are all greater than 0, right? Okay, next consider some rational numbers. Okay, m by n, where n belongs to natural number and m is an integer. Okay, so any rational number can be written this way, right? Any rational number can be written as this. So as a consequence of field properties, already we have seen, if we have some numbers like 1 by minus a, this number, this can always be written as minus of 1 by a. Okay, so these things we can do. So any rational number, we can write it as m by n, where n, we can take the denominator n to be positive. Okay, because if the denominator is negative, say something like 3 by minus 2, so we can always write this as minus 3 by 2. Okay, we have already done this result. Okay, so a by minus b is something like minus a by b. Okay, already we had seen this result also. Yeah, minus of a by b is minus a divided by b. Okay, a 1 by minus a is minus of 1 by a. Okay, so those things we can use, right? So any rational number can actually be written in this form, where the numerator is an integer and the denominator is a natural number. Okay, so let us see under what condition a rational number will be rational number written in this form will be positive or negative. So if m is greater than 0, then by order property, so we have this n is a natural number, so since n belongs to natural number, so 1 by n is greater than 0. Okay, and if m is greater than 0, then by order property we have m into 1 by n. This is also greater than 0. So that is, but m into m by n is the notation for m into 1 by n actually. So that is m by n is greater than 0. Okay, so we know under what condition a rational number is positive, if the numerator is positive. Okay, means provided that you express it something like means if you express it in the form where the denominator is positive. Okay, so if we make the denominator positive, then just by looking at the numerator we can conclude that whether the rational number is positive or negative. Okay, if m is less than 0, okay, then minus m is greater than 0. So by order property minus m multiplied with 1 by n, this is greater than 0. So that is minus m by n is greater than 0, right? But minus m by n is same as minus of m by n. So minus of m by n is greater than 0. So by this law of trichotomy, the third order property, it follows that m by n is less than 0. Okay, because only one is true. So minus of m by n is greater than 0. So that means m by n has to be less than 0, right? Okay. So we know under what condition rational numbers are positive or negative. Okay, the problem still remains with irrational numbers. Okay, we have not done anything about irrational numbers so far, but of course we will do it. Okay, so let us use these things to do this exercise. Show that there cannot exist any smallest positive real number. Okay, we cannot find out any smallest positive real number. Okay, right? Suppose you say that 0.001 is the smallest. No, this is not the smallest, because there are other numbers which are smaller than this. Okay, I can just keep on increasing the number of zeros before 1. Okay, so actually nobody can find the smallest positive real number. Okay, right? So how we can see this quick justification using the order properties. Okay, suppose that A belongs to R is the smallest positive real number. Okay, so A is greater than 0. Okay, and we know so can you find a real number which is smaller than this and also positive? Okay, so we will make use of this fact, this 1 by n. 1 by n is positive. Okay, so what are the numbers smaller than A? So if we just keep on dividing by natural numbers, then we get smaller numbers, right? So that is the idea basically. So we know half is greater than 0. So by order property we see A into half, this is also greater than 0. Okay, so that is A by 2. So this is the notation for A into half. A by 2 is greater than 0. So we have got a number A by 2 which is a real number. Okay, and it is greater than 0. Now we have to check whether A is greater than A by 2 or not. Okay, or A by 2 is less than A or not. Okay, we have supposed that A is the smallest. Okay, that means we cannot find anything smaller than A. Okay, but we will show that the number a by 2 that we have found is actually smaller than a. Okay, so now, so how to show that a is greater than a by 2? We have to just compute the difference of these two, right? A greater than b. In order to show this, what is the definition? Definition was a minus b should be greater than 0. Okay, so we will compute this. Now a minus a by 2, this is what equal to a by 2 only. Okay, because it's something like a into 1 minus a into 1 by 2. So it's the distributive law, 1 a into 1 minus half, so it is a by 2. Okay, 1 minus half is half. Okay, that is a by 2, right? So that way a minus a by 2 is same as a by 2. Okay, now a minus a by 2 is a by 2, but a by 2 is already greater than 0. Okay, so a is strictly greater than a by 2. Okay, thus a by 2 is a positive real number that is lesser than or smaller than a. Okay, so what is the problem then? We have claimed that a is the smallest positive number, but immediately we have shown that a by 2 is a number which is also smaller than a. Okay, that means our claim is incorrect. Okay, this claim is incorrect. A cannot be the smallest. Okay, so thus a by 2 is a positive real number that is smaller than a. Hence, the claim that a is smallest is incorrect. Okay. A is smallest is incorrect. Okay, right? So there cannot exist any smallest positive real number. Okay, we cannot say anything like, yeah, I have chosen the smallest positive real number. Okay, that cannot happen. Okay, so if somebody comes up with a claim that, yeah, we have found out a smallest positive real number, so instead of sharing it in social media, just give this particular justification. No, whatever smallest number you have got, it can means your claim is incorrect, because I can find a smaller number than that. So what I have to do, just I have to divide the number that you have got. I just divide that number by 2. Okay, then I will get a number which is smaller than the number that you are claiming to be smallest. Okay, so we cannot find out smallest positive real number. Okay, that is the thing. So in terms of this number line, you see this here we have something called 0, then something called 1, 2, 3, like that. Okay, here we have the negative numbers, minus 1, minus 2, minus 3. Okay, so if we draw geometrically that in the diagram, it appears that, yeah, as we move towards this 0, we are getting smaller and smaller number, and at some point we will get the smallest positive real number, but that is incorrect, because already we have shown why it is incorrect. Once you come up with a smallest number, suppose you have come up to this, let us magnify. So what we are doing is magnifying this part. Okay, so suppose you have come very long way and you are claiming that, yeah, this is the smallest. You are tired now and you are claiming that, yeah, I have got the smallest number. Okay, but immediately in the next moment we will give you, no, this is another smaller number than a, so a cannot be the smallest, right? Then okay, you tell us that yeah, let us agree that a by 2 is the smallest. Okay, but again we can give you another number which is smaller than a by 2. What is that? A by 4. Okay, so given a by 4, we can again come up with another number which is smaller than a by 4. Okay, so that way it will continue, a by 16, a by 32, like that. Nobody can claim that he has got the smallest real number. Okay, it's not correct. So there are so many real numbers here, but of course the smallest non-negative real number is there. Smallest non-negative real number is 0. Okay, if we say non-negative. If we say positive, then there is no smallest positive real number. If we say non-negative, then 0 is there. Okay, nothing can be smaller than no non-negative number can be smaller than 0. Okay, because once it is smaller than 0, it is a negative number. Okay, right. So there is another theorem which is also very important, and it will be used in several proofs. Okay, so if a belongs to real numbers such that 0 less than or equal to a, strictly less than epsilon for all epsilon greater than 0, for every epsilon greater than 0. Okay, let me write it in language. For every epsilon greater than 0, then this a has to be 0 only. Okay, if a is a real number, non-negative real number, which is smaller than every positive real number. Okay, right. So let me write it in language. If a is a real number, a is a non-negative real number, non-negative real number that is smaller than every positive real number. A is a non-negative real number that is smaller than every positive real number. Then this a is nothing but 0. Okay, so 0 is the only non-negative real number which is smaller than every positive real number. Okay, we can have this as less than or equal to epsilon also, that's not a problem. Okay, so let us maintain one standard. We'll just consider strictly less than epsilon. Okay, right. So how will you prove this? So this epsilon is a symbol which is very much favorite of mathematicians. Okay, so epsilon usually we use epsilon to denote any arbitrary positive real number. Okay, so if a belongs to real number and a satisfies that whatever positive number you take, a is less than that positive number, then a has to be exactly equal to 0. So it is given that a is greater than or equal to 0. Okay, so either a is greater than 0 or a is less than a is exactly equal to 0. So if a is exactly equal to 0, our proof is complete. Okay, if we know that a is already positive, then we don't have to prove anything. Okay, so what I have to prove is if somebody claims that a has to be greater than 0, then I have to bring some logical ideas to show that that cannot happen given a greater than or equal to 0. So if a is strictly greater than 0, okay, then what happens? So we will use this earlier argument. Okay, the earlier argument that we have used here, this one, where is it? Yeah, there cannot exist any smallest, that argument. Okay, so we will use that argument. So given a greater than or equal to 0, if a is strictly greater than 0, then what happens? Then the real number a by 2, then a by 2 is a real number, and a by 2 belongs to R, and a by 2 is greater than 0, as half is greater than 0. Okay, as half is greater than 0. So we have something like so 0 less than a by 2 less than a. Okay, we have got a by 2 greater than 0. Also a minus a by 2 is equal to a by 2, which is greater than 0. So we have got 0 less than a by 2 less than a. Okay, but this contradicts. A by 2 is a positive real number, but as per our hypothesis, a should be lesser than every positive real number. Okay, but here we get something different. Okay, so our idea is, or the hypothesis becomes false. Okay, right. Yeah. So 0 less than a by 2 less than a, but this is contrary to our hypothesis. This is contrary to the hypothesis. This is that a is smaller than every positive real number. Thus, our assumption is incorrect. What was our assumption? Assumption is a greater than 0. Okay. So if a is greater than 0, immediately we get this problem here. Okay. So thus a greater than 0 cannot happen. Okay. If a is a number which satisfies this condition, then a can never be greater than 0. So thus the only option is a has to be equal to 0. Okay. So if you have a number which non-negative real number which is less than every epsilon, okay, then that number has to be 0. Okay, nothing else, right? That number has to be exactly 0. Okay, so this is a very important result which also will be used several times in real analysis. Okay, let us see another theorem. So we know that the product of two positive real numbers is positive. Okay, now the other way, if you are given two real numbers as the product is positive, then what can you say about the numbers? Okay, so the theorem is, if a comma b belongs to R such that a into b is greater than 0, okay, such that a into b is greater than 0, then either a is greater than 0, b greater than 0, or a less than 0 and b less than 0. Okay, means either both are positive or both are negative. Okay, either this or this. Okay, means that is either both are positive or both are negative. Okay, so let me just write comma means and only. Okay, a greater than 0. Okay, let me write and only so that you don't get confused. So either a greater than 0 and b greater than 0, or a less than 0 and b less than 0. So either both are positive or both are negative. Okay, so how will you prove it? Proof is this simple. AB is given to be greater than 0, so implies that A is non-zero, B is also non-zero, because already we have proved one result that if AB is 0, then either A is 0 or B is 0. Okay. And if any one of A and B is 0, then their product has to be 0. Okay, right? Okay, so let us. Okay, so if given A into B is greater than 0, okay, so if A equal to 0 or B equal to 0, okay, then AB is equal to 0. Okay, by properties of real number. Okay, by field properties, field axioms. Okay, 0 multiplied by follows. We have already done this. Follows from field axiom. 0 multiplied with any real number is 0. Okay, we have already done. So if A equal to 0 or B equal to 0, then AB equal to 0. Thus, so we are given that AB is positive. Okay, so A and B cannot be 0. So thus A not equal to 0 and B is not equal to 0. Okay, A and B are both non-zero. So by law of trichotomy, so A cannot be 0. So law of trichotomy says that either A is 0 or A is greater than 0 or A is less than 0. Okay, so by law of trichotomy, either A is less than 0 or A is greater than 0. Okay. So let us see if A is less than 0, then what happens. If A is less than 0, then we have minus A is greater than 0, right? So 1 by minus A. Okay. Or directly we can write, if A is less than 0, then 1 by A is also less than 0, right? We have already seen, or we have seen it for, the proof is similar. Okay, so we can just use it here. I'll just let you know how it happens. If A is less than 0, then 1 by A is also less than 0. So this B, which we can write as A into 1 by B. Okay, this B can be written as AB multiplied with 1 by A. Okay, AB into 1 by A. So this product, it can be written as what? This product will be negative. Okay, because this is multiplied with a negative quantity. Okay, we have already done this, no? A greater than B and C greater than 0, then CA is okay. If A is greater than B, then C, and C is less than 0, then CA is greater than CB. Okay. Okay. We have not exactly done that. The product of positive and negative is negative. Okay. We'll just do it in one line so that it's clear. So for the time being, let us continue with this proof. So if A is less than 0, then 1 by A is less than 0. So B equal to this AB into 1 by A. So this is going to be less than 0. Okay. So B equal to this is less than 0, as AB is greater than 0. Okay. AB is greater than 0 and 1 by A is less than 0. Okay. Okay. This way we can do, or let us do it in a different way. Let us do it in a different way. Okay. So by law of trigonometry, either A is less than 0 or A is greater than 0. So if A is less than 0, then we have minus A is greater than 0. Okay. So 1 by minus A, this is also greater than 0. Okay. And then by order property, we have AB into 1 by minus A, this is greater than 0. So that is, but AB into 1 by minus A, that is actually minus of this A into 1 by A into B. Okay, this is greater than 0. That is minus B. So A into 1 by A is again 1. So minus B is greater than 0. That is B is less than 0. Okay. So if A is less than 0, then B also is less than 0. Okay, right? And so we have to check the other condition, that what happens when A is greater than 0. Okay. So next part is, if A is greater than 0, then 1 by A is greater than 0. And so by order property, we have A into 1 by A into AB, this is also greater than 0. So that is 1 by A. So just associative property dot B is greater than 0. That is B is greater than 0. Okay. Thus AB greater than 0 implies A comma B greater than 0, or A comma B, they are both less than 0. Okay. So this is the thing. Okay, this is what we have proved, right? See, if you see the proof again, given that AB is greater than 0, so if A is equal to 0 or B equal to 0, then AB is equal to 0. So thus this cannot happen. Okay, thus A should not be equal to 0, B should not be equal to 0. So by law of trichotomy, since A is non-zero, then there are two possibilities: either A is greater than 0 or A is less than 0. So if A is less than 0, then minus A is greater than 0. So minus 1 by minus A is greater than 0. So by order property, we have this AB into minus 1 by minus A this is greater than 0, so that is minus b is greater than 0, that is b is less than 0. Okay, so this whole part again we can do it simply. Just let me do one result. Previously I forgot to do this exercise also. If a comma b belongs to R, if a comma b belongs to R, then such that, so if both are positive, then number one, this property, if a greater than 0 comma b less than 0, this will imply a into b is negative. Product of positive with negative is negative. Okay, and number two, product of this negative with negative, a less than 0, b less than 0, this will imply that ab is less than 0. Okay, so the solution is very simple. Given a is greater than 0, b is less than 0, so this implies a is greater than 0 minus b is greater than 0. So by order property, a into minus b, this is greater than 0, so that means minus of ab is greater than 0, so that means ab is actually less than 0. Okay, so it's a very simple thing, but I forgot to do it in the earlier class, so we actually need this result. So given a is less than 0, so this is the first one. The second one is here, a is less than 0, b is less than 0, so this will mean that minus a is greater than 0 and minus b is greater than 0, so this will imply minus a into minus b, this is greater than 0, so this follows from order property. But minus a into minus b is by field axioms, it's ab, so ab is greater than 0. So product of negative numbers is here this is positive, right? Product of negative numbers, two negative numbers is positive. Product of a positive and negative number is negative. Okay, so so this result we can use it here. Instead of doing it in a complicated way, let us do it in a simpler way. Okay, so if a is less than 0, then 1 by a is also less than 0, and so this 1 by a into ab. Okay, but ab is given to be positive, so but 1 by a is negative, so 1 by a into ab, positive into negative will be negative, is less than 0, so that is that is 1 by a into b is less than 0, that is b is less than 0. Okay, so if a is less than 0, then b is also less than 0, right? The next part also, a is greater than next part is okay. Yeah, so this is the proof. So in this earlier one, please cancel the earlier thing that I had given. You can just write this part. Okay, right? If a is negative, then 1 by a is also negative. So product of 1 by a with ab is negative because ab is positive. Okay, so that is what, right? So this exercise also, small exercise, you can try. I think these were given in this. Show that if a is greater than 0, then 1 by a is greater than 0. Okay, this was there in the exercise, but I did not do it. Okay, so show that if a belongs to R with a greater than 0, a positive, okay, then this 1 by a has to be positive. Okay, so this is also a small exercise, we can do it very simply. So it's given that 1 by a is greater than 0. Okay, so suppose 1 by a is negative. Okay, so then minus 1 by a will be positive. Okay, so therefore by order property we have a into minus 1 by a, this is positive. Okay, so this implies minus 1 is positive, which contradicts, okay, which is contrary to 1 greater than 0. So thus 1 by a has to be greater than 0. Okay, So if A is positive, 1 by A has to be positive. So we have proved it, right? Another exercise, the arithmetic mean. No? Show that if A is strictly less than B, then A is less than A plus B by 2 less than B. Okay. Right. So if we have two real numbers A and B, then A plus B by 2 is also a real number which lies strictly between A and B. Okay. This arithmetic mean of these two lies strictly between them. Okay. So the solution is actually simple. You have this. Yeah. Okay. So given A is less than B. So A less than B means what? B minus A is greater than 0. Okay. B minus A is positive. So now in order to show this inequality, what I have to do? I have to find out the difference of A plus B by 2 and A. Okay. So now A plus B by 2 minus A. If I can show that this is positive, then this inequality is correct. A plus B by 2 minus A is actually what? A plus B by 2 minus A. Okay, is actually same as B minus A by 2. Okay, so it is B minus A into 1 by 2. Okay, which is positive. Okay, since half is also positive. Okay, half is greater than 0. Half greater than 0 and B minus A is greater than 0. Okay, so this minus this is positive. That means A is strictly less than A plus B by 2. Okay, right. Similarly, the other one. Similarly, this one, B minus A plus B by 2. Okay, this one. This is equal to B minus A by 2. Okay, which is equal to B minus A into 1 by 2, which is also greater than 0. So A plus B by 2 is strictly less than B. Okay, so this is the simple proof, just using the definition of less than and greater than. Okay, right. Okay, so between any two real number there exists just one real number. Okay, there lies at least one real number. Okay, right. Okay, so let us see some other examples. Yeah, this one, this exercise. Try. If A comma B belongs to real number, show that A square plus B square equal to 0 if and only if A equal to 0 and B equal to 0. Okay, so if this happens, only when A square plus B square is 0, if and only if A equal to 0 and B equal to 0. Okay, right. So there are two parts. First we will suppose that A square plus B square is exactly 0. Then we will try to show that A equal to 0, B equal to 0. The other one is if A is 0, B is 0, then A square plus B square is 0. Okay, so these things we need to show. So let us start with the other part now. Okay, if A equal to 0 and B equal to 0, then what is A square? A square is 0 into 0, which is equal to 0. B square is 0 into 0, that is 0. Thus A square plus B square, this is equal to 0 plus 0, so which is also equal to 0. Okay, right. So one part we have shown. The other part is Conversely, let a square plus b square equal to 0. Okay, right. So if a square if a is strictly greater than 0, okay, then what happens? We had done one result last day that if a is non-zero, okay, not only for strictly greater than 0, we have done it for non-zero also. If a is not equal to 0, then a square is actually strictly greater than 0. Okay, this result already we have done. It follows from the trichotomy property. Okay, if a is non-zero, then a square is greater than 0. Okay, so just let us have a look at it again. If a is not equal to 0, then by trichotomy property either a is less than 0 or a is greater than 0. So if a less than 0, then a into a will be greater than 0, that is a square is strictly greater than 0. If a is greater than 0, then a into a is greater than 0, that is a square is greater than 0. Okay, so thus a not equal to 0 actually implies that a square is strictly greater than 0, right? So a square plus b square will be strictly greater than 0, right? Since b square is greater than or equal to 0. Okay, square of any real number is non-negative. Okay, so this which is contrary to our hypothesis. Okay, which is contrary to our hypothesis. Thus a has to be equal to 0. Okay, if a is not equal to 0, then there is a problem. Okay, we get a square plus b square is strictly greater than 0. So thus a should be equal to 0. Similarly, b also has to be equal to 0. Okay. So we have proved if a is equal to 0, then if a square plus b square is 0, then the only option is both of these numbers have to be 0. Okay, a and b both have to be 0, right? Okay, so I'll give you some exercises which you may try. Okay, please try exercise so that if 0 less than c less than 1, show that 0 is less than c square less than c less than 1. Okay, if c is a real number lying between 0 and 1, then c square is actually strictly less than c. Okay, this one you try to show. Also you try to show that if c is greater than 1, then 1 less than c square. Okay, so if c is a real number which is greater than 1, then when you take c square, you will get something greater than c. If c is less than 1, then c square will be less than c. Okay, that is what you try to show this. Okay, another one which you may try. Okay, square root we have not done. Okay, you try this. Determine the set. So we have to use properties of inequality. Okay, determine the set b equal to set of all those x in R such that x square plus x is greater than 2. X square plus x is greater than 2. Okay, so try to determine this, right? X square plus x is greater than 2, so you find out for which values of x, and so you have to describe this particular set. So you have done this similar problem in higher secondary also. Try it. Okay, another one you can try. Determine the set C equal to x belongs to R such that twice x plus 1 divided by x plus 2 is strictly less than 1. Okay, we try to determine this to set. Okay, so in the next lecture we will do something about the absolute values of real numbers, and then the upper bound, lower bounds of real number. Okay, we will do some properties of the modulus function. Okay, that is the absolute value of a real number. Okay, so that is also very much important for our real analysis. And okay, we'll join for a live session also. I have given the link in. I'll give the link in your Google Classroom. Okay, thank you.